Hello and welcome to today's lesson. This is Mr. Kaonga Samuel. Wherever you may be watching me from, you are in Form 1, you are in grade 9, you are in grade 10, you are in grade 11. This is really a place to be. I welcome you to this channel and to today's lesson. As you can see on your screens there, today we are going to concentrate on a topic called approximation. Wondering how to go about approximation? Then wonder no more, because this video is going to answer your questions. Right. If you are new to this channel, please go ahead and like this video and give it a thumbs up, and don't forget to hit that bell notification icon so that each time I upload a new video, you are going to be notified. Really, let's dive into the lesson for today. We'll start by looking at error and accuracy. Error and accuracy. You'll discover that when we count, the result is always true and accurate. For example, we can say how many desks are in this class. We can say, okay, let's count. There may be 1, 2, 3, 4, 5 desks. How many tables? There are 2 tables. That result is always going to be true and accurate. However, this is not the case when you do a measurement, right? For example, people may be given, may be told to measure maybe 5 centimeters. So many people are going to, different people are going to come up with different results. Maybe some are going to measure maybe 5.1, others 5.2, others 4.9, still others 4.99. Yet what we want is 5 centimeters. So you discover that if you are doing a measurement, it is not always true that your result is going to be accurate. For this reason, measurements are bound to errors. Okay, measurements are subject to errors. Right, let's jump into another slide and see what is there. We are going to consider now the key definitions that govern approximation. Key definitions. Definitions are so important in mathematics, because part of the answers that you're looking for, they'll always come from definitions. So the first definition that we're going to look at is, what is a dimension? What is a dimension? A dimension, as you can see, is simply a measurement. A dimension is a measurement, right? What is an interval? An interval is the range in which a dimension is going to lie. Okay? If we are looking at an interval, then we have to consider the upper bound and the lower bound. So let's look at an upper bound on the upper limit. This is the biggest number of an interval. It is also called an upper bound, or the greatest possible measure. Lower bound or lower limit. This is the smallest number of an interval. It is also called the lower bound or the least possible measure. Now, what is important for you to note is that we can use words like the greatest possible measure, the upper limit, or the upper bound to mean the upper limit or the greatest possible measure or the biggest number of the interval. So this you need to take note. Different authors, they will use different languages on this topic. Let's jump into another slide and see what is there for us. Before we jump into that one, let's look at tolerance. Tolerance is simply the difference between the upper bound and the lower bound, or the upper limit and the lower limit. That is what we're going to call tolerance. Okay. Right, here we are into this symbolic representation slide. Okay. Now a dimension is represented by true value plus minus error. Error is given by the formula plus minus n over 2, where n is the unit of measure. N is the unit of measure. Great. So there's also a way of representing these dimensions in an interval notation or the inequality form, which is very simple. I'll show you as we go on. So that is in symbolic notation. That is how it may look. Okay, meaning we are going to have upper limit is equal to dimension or true value plus minus e, or lower limit is going to be dimension minus error. Okay, so tolerance is now going to give us upper limit minus lower limit there, or simply tolerance is going to be 2 by absolute error. Now take note, this tolerance is equivalent to the unit of measure. So the value for unit of measure and tolerance, they are exactly the same. Okay. Let's look at this useful table that is going to help us. It's a summarized table that is going to help us understand how we can relate error, the language to the nearest, and the unit of measure, and what will be the absolute or the maximum error. Okay, so take note of the in the table, the language to the nearest. We are relating this language to the nearest with n being the unit of measure. So now, when we say the question, or when the value is rounded off to the nearest 1000, this is a whole number. It simply means the unit of measure is going to be 1000, and the maximum error is going to be unit of measure over 2. In short, 1000, in this case 1000 over 2. So on 1000 we're going to have the unit of the maximum error of plus or minus 500. Now straight to the decimal numbers. Any number that is written to the nearest one decimal place, to the nearest, take note of the language to the nearest one decimal place, it simply means it has the unit of measure of 0.1. 0.1. Why? A number written to one decimal place is written to the nearest tenths. That is where we are getting this 0.1 from. It is a tenths. That number is written to the nearest tenths. So because it is written to the nearest tenths, then it is going to have the error of, or the maximum error of plus or minus 0.05. Where are we getting the 0.05? It is gotten from the formula. Error is equal to plus or minus n over 2. Great. The same applies to a hundredths. The unit of measure is going to be 0.1. A number written to 3 decimal places, meaning to a thousandths. So our unit of measure is going to be 0.001. Hence, our error is going to be 0.0005. Right. Next slide. Okay, I think I've explained language. Okay, language I've explained to the nearest. Tenth means 1 decimal place, and our unit of measure is going to be 0.1. The same applies for a hundredths. Unit of measure is going to be 0.01. The same applies for a thousandths. Number that is written to a nearest thousandths, it means it is written to 3 decimal places. That number is going to be to have a unit of measure of 0.001 in value. Great. Let's look at examples. So example number 1, calculate error on the following measurements. So error on 10.4. So take note, 10.4 is written to the nearest 1 decimal place. So what do you think the unit of measure is going to be? The unit of measure is going to be 0.1. Exactly. So why is it 0.1? Because it is written to the nearest tenths. A tenth is 0.1. So error there is going to give us plus or minus 0.05. 105 kg to the nearest 10. The unit of measure is 10. The unit of measure is going to be 10. So error is going to give us what? Unit of measure over 10. So 105 is going to be permitted to have an error of 5 kg. 12 to the nearest integer. So to the nearest integer, we're just looking at this being to the nearest integer. It is going to have error of, the unit of measure is going to be 1 there. The nearest integer 1 is going to be our unit of measure, and this you're going to see it illustrated in the solution slides. And here we are, solution to the above questions. So nearest tenths, n is 0.1, I've already explained. Error is going to be 0.1 over 2, hence error is going to be plus minus 0.05. That is on 10.4. Then on 12, this is for 12, error is going to give us integer, the nearest integer n is 1, so error is going to give us 1 over 2, which is 0.05. Okay, on 105 to the nearest 10, so to the nearest 10, n is 10, and hence the 5 kgs there. Great. Let's jump into example 2. Example 2. This might happen to be our last example. The mass M of a bag of potatoes is 12 plus minus 0.5 in brackets kgs. Calculate the upper limit. So when a question has been given to you like so, as you can see on your screen there, where 12 plus minus 0.5, straight away notice that this is plus minus 0.5. This number here is indicating the absolute error. So in this question, error has been given to you in advance. It has been calculated for you. There is no need for you to calculate error because it has been calculated for you in advance. Calculate the least possible mass of the bag, then calculate the tolerance, and then represent the mass in the form, in the inequality notation there. Let's jump into the slide solution. The solution slide. Now take note here, you discover that this 12 is the true measure or the true value. True value is 12. Then the plus minus 5 is error. So for us to find the upper limit, you can even guess. Upper limit is going to be true value plus 0.5. So we're going to have 12.5. Least possible measure is the same as lower limit. Tolerance is going to be 2 by absolute error, or simply upper limit minus least possible mass. Great. Solution. Here we are. From the given dimension, error is going to be plus minus 0.5 kg and the true value is 12. Therefore, upper limit is going to be true value plus error. So upper limit is going to give you 12 plus minus 0.5, which is going to give us 12.5 kgs. Okay, least possible mass, which is equivalent to lower limit mass, is going to give you dimension, take away error, which is 0.5. So our true value is 12. Now to this 12, we are subtracting a 0.5, which is going to give us 11.5. Hence, tolerance is simply going to be 2 multiplied by absolute error, which is going to give us 2 multiplied by 0.5. Hence, our tolerance is going to give us 1 kg. This has been approximation part 1. Watch out for approximation part 2, where we're going to look at relative error, percentage error, and absolute error in a little bit more detailed manner. Thank you for watching. Please do not forget to like this video, to hit that bell notification, and indeed to share this video to as many people as possible so that we can grow this channel. With love, goodbye.